G'day, in this video we're going to be looking at the basics of kinematics. Again, kinematics is all about the measurement and analysis of motion. In this video, we're really starting to delve into some key dot points. Our focus today is 1.1.1, the first content dot point. Comes from Module 1 Kinematics. Its focus is on inquiry question 1, which is looking at how the motion of an object moving in a straight line can be described and predicted. And then we're looking at our content statement number 1, which is describing uniform straight line rectilinear motion and uniformly accelerated motion through some qualitative descriptions, qualitative meaning descriptive or worded descriptions, not numbered or measured descriptions, and also using scalar and vector quantities. We're going to come across those two words shortly, but notice that we have some qualitative ways of being able to describe motion and some quantitative ways of being able to describe motion. That's our focus for today. So we're going to be defining what rectilinear motion is. I just read that a second ago, might not have heard that word before. Look at scalar and vector quantities as well, and what the differences are between them. Then define and identify the pronumeral and units of measurement for a bunch of different types of measurements that we take for kinematics, and that is time, distance, displacement, speed, velocity, and acceleration. So first off, rectilinear motion. You'll notice that part of the word here includes the term linear. When we're talking about something that's linear, we're looking at straight lines. Funnily enough, rectilinear motion refers to motion that's happening in a straight line. Straight line motion is the most simple motion to describe, understand, to measure. So that's where we're going to be starting in this first inquiry question. Now, scalar and vector quantities may not be terms that you've heard of before. In short, scalar measurements have a size that we can measure. They have an amount. Maybe you've seen or heard of the word magnitude, but there's no direction to this measurement. Whereas vector measurements, they have a magnitude, they have a size, something that we can measure, but we also have to describe their direction. Now, that concept may not make a whole world of sense yet. It's one of those things that are a lot easier to describe with specific examples of scalar and vector measurements, which is what I'm going to do now. We might come back to these definitions when we start our class. First measurement that I'm going to be looking at is time. It's a measurable period where something can occur. Yes, technically something could also not occur during a period of time. It has a pronumeral t. That is usually how you will see time represented in formulas. The SI unit, which is the International System of Units, meaning the standard common unit, the default unit of measurement that we use for time is seconds. There are other units of measurement for time, but seconds is the one that we always do by default. Now, it is a scalar quantity. Reason being that we can measure the size of time, but time doesn't have a direction. It always moves forward. There is no negative time as such. Note also that we can show delta t as a way of representing time. The Greek letter delta here represents change. So you won't just see that for time, but in lots of different circumstances. If you've not seen delta before, delta means change. We generally write it with that triangle. That is the capital of the Greek letter delta. So delta t can be shown as time changes. So what delta t usually measures is the change of time or the progression of time. Now, this value we usually have to calculate. Sometimes we can just subtract the finish time from the start time. So if I start something at 4 o'clock and end at 4:05, delta t would be 5 minutes, finish time minus start time. Sometimes we talk about delta t or the change in time as the sum of time for all steps. So I do something in 10 seconds, I do another thing in 15 seconds, and I do another thing in 20 seconds. In total, the change in time or the time that's progressed is 45 seconds, but usually delta t is something that we calculate based on the context of a question. We also have distance. Now, this is the amount of space that's traveled by an object, and we use this term called actual path. I'll come back to what that means in a second. Now, there are many pronumerals that can be used to show distance depending on what text you're actually looking at. Sometimes it's d, not so common. Sometimes it's s, but that can be conflicting with the next measurement that I'm going to look at, displacement. Sometimes it's just written as distance. And the SI unit is m, or meters. It's a scalar quantity because we can measure the amount, but we don't put a direction with distance. That's going to be displacement, which we'll look at in a second. Now, because it's not usually used in the course and it's not something that we actually use very much, sort of our more hardcore physics, to keep it safe and to sort of distinguish from displacement, which I'm going to talk about in a little bit more in a second. If you're ever using distance in a calculation, I would recommend just writing it out to avoid confusion for yourself or confusion from your reader who might be looking at a problem that you're solving. Now, displacement is similar to distance. It's still the space between an area that's being traveled, but specifically we're looking at the distance between a starting point and finish point, and we call it the straight line path. I'm going to draw what I mean by actual distance or actual path and straight line path in a second. Now, for displacement, we might see pronumerals as S or S with an arrow over the top. Now, the arrow is here because it is a vector quantity. You may see some differences in different texts. When this course was being developed a handful of years ago now, originally a lot of these vector quantities were given this arrow, and this is a way that you can show and represent a vector quantity. I think they kind of went back on it right before the HSC started. So some texts you'll find, again, have the arrow, some don't. In the data sheet that we'll be spending a lot of time looking at, most pronumerals don't have an arrow, displacement being one of them. So as a default, you're probably better off going for S without the arrow, but if you see this, you know what it means. We also measure displacement with the SI unit. Meters, that's the standard unit. It's a vector quantity, as I said before. The direction must be given when we're showing displacement, this straight line path, the direction of travel. So, actual versus straight line path. Easiest way to explain the difference between distance and displacement is to actually show it. So I'm going to put down 2 points on the page here. We've got point A and we've got point B. So A is going to be our starting point, B is going to be our ending point. Now when we travel, we don't usually travel in a straight path. We can, but it doesn't happen a lot of the time. Think about roads. They may be straight for some parts, but generally when we're traveling from one place to another, we don't go in a straight line. So what might actually happen traveling from A to B? Maybe something like this. That might be the path that is traveled. Now we would say that this is the actual path of travel. And we could measure how far a person or an object has traveled along this path, and that would be its distance, the amount of space that's been traveled by the object. However, when we're working in physics, it's generally not something that we focus on too much. Usually we're much more concerned with how much space there is between A and B. And this would be the straight line path. And this is what we call displacement. So displacement is the straight line path, the distance between the starting and the ending point. And the actual distance, or the actual path, is the path traveled by the object. May not be just the straight line. And generally speaking, the distance is going to be bigger than the displacement in that sort of scenario. Next measurement that I want to look at is speed. Now this is the actual distance traveled in a period of time. So we use distance, not displacement in our calculation. We just looked at that at the lesson prior. Again, there can be some confusion about the pronumerals. That's generally because we don't look at speed a lot. Actually, we look at its vector counterpart, velocity. So you may see speed as S, you may see it as V, but good general rule, if you're talking about speed or you're writing it mathematically, you're probably better off just writing it out because, again, it's not something that we look at too much, and that will hopefully avoid any confusion. Now, we measure speed in meters per second. You may start to see units of measurement using this index notation. I'm going to go through that in class a little bit more when we get in to sort of explain why that is, but you may see ms to the -1 for meters per second. We'll look at that a little bit more depth in class. It's a scalar quantity, meaning that we can measure the amount of speed, but there's no direction attached to it. It's just an amount. And again, not used all that much in this course. We look more at velocity, which is the vector quantity. Again, if it's a vector quantity, one of the big differences between scalar and vector, we must show the direction when we're looking at reporting velocity. And it is the straight line distance, so the displacement traveled in the period of time. And we'll use the pronumeral V. Again, there may be some texts that show the pronumeral with or without that little arrow. In the data sheet, V is what you're going to be using without the arrow. It's also measured in meters per second. Now, the comparison that we can make between speed and velocity is really quite similar to the comparison that we make between distance and displacement, but we'll have a look at unpacking that a little bit more in class next period. The last measurement that I want to look at is acceleration, and that is the change in velocity over a period of time. In other words, speeding up, slowing down, but because velocity is vector, it could also mean changing direction. Now that's a little bit more of a complicated aspect of acceleration, not something that we're going to focus on too much at the beginning, but acceleration comes up over and over and over again throughout the course. So hopefully that idea of acceleration and changing direction makes sense as we go along. For numeral A, or A with an arrow, again, a lot of the arrows have been removed. A is generally what we're going to be using because that's what's in the data sheet. If you see the arrow, you know why it's there. Looks like I made a little bit of a typo with our SI unit. Generally, we would write here meters per second squared, or maybe something like meters per second. Essentially, what that means is I sort of bundle this little bit here. Meters per second is our velocity. So that's how fast something is going in a particular direction. When we're accelerating, if we were to speed up, there would be an increase in velocity every second. And that's something that we can calculate in a different video as well. There could be a decrease in velocity, a decrease in the meters per second travel. And that could be happening really fast or really slow, and that could be changing every second. One way that we can observe acceleration is seeing a speedometer change. So we have our speed shown here, no direction, so technically it is speed. So when we see acceleration that's increasing, we'll see the needle moving up. The quicker the needle moves, the quicker the acceleration. The slower the needle moves, the slower the acceleration. The same can be said when slowing down is happening. That's just acceleration sort of in the opposite direction. In this table, you might want to refer to it later. It just has a summary of those measurements, the common pronumerals that I recommend that you use based on what's on the data sheet, the units of measurement that goes with it, and whether or not they're scalar or vector quantities. When we get into class, we're going to consolidate what scalar and vector mean a little bit more and start to break down these concepts of distance, displacement, speed, velocity, acceleration. Now in the next video, our focus is going to be on measuring and calculating velocity and acceleration a little bit more, so getting a little bit further into depth. Now there's two types of velocity that we're going to be looking at, instantaneous and average. We're going to be, again, deep diving into acceleration, what it means, how it's measured, how it's calculated, etc. in much more depth. See you in the next one.